Last video we derived the equation in this equation sheet, and then now we're gonna derive the equation that describes um, subcritical damping, which is also, in other words, under damp. Okay, so let's start. So last lesson, last whatever, we stop here, and then now we're gonna talk about 8, 9, 10, and 11, which is like anyway. So yeah, so P and Q. Okay, now this is a very complex. Not whatever. So P and Q are set by initial condition. Okay, you have to first. This is the most like somewhat theory part lah. Okay, so P and Q are set by initial condition. What I mean by P and Q is set by initial condition is that A plus B is equals to P, right? You know that A and B, if you were to remember last time when you solve for differential equation, A and B, the values of A and B can only be found when you sub in your initial conditions. So A and B itself is dependable on the initial condition, and therefore P itself is also dependent on condition, and since Q is also depends on A minus B, also in terms of initial condition, therefore P and Q are set by initial condition. This is what I mean. Okay, so when you sub in whatever initial condition, okay, we take this as a rule of thumb. And when you sub in whatever initial condition, we believe if you sub in any initial condition, you get A and B. Thus, this relationship can be described using phase shift. Okay, what do you mean by phase shift? Okay, if your initial condition starts with a certain velocity, right? You let's say if your initial condition start from certain velocity and certain displacement. Let's say we have a graph over here. And okay, maybe it starts from here. Okay, you choose to start from here, and it goes wherever shape you want. Okay, instead of here. Okay, typically we start from here, right? Because when you pull the mass, when you pull the mass down and you release, when you pull the mass down, you have a certain x distance, right? From wherever data point you are referring to, and you release, you'll start to go back, you start to spring back up. Okay, so sorry, I didn't draw it properly. This should be it. Yeah. So when you initial mass position is here, and when you pull this down, it's in this position, and you release, it oscillates back up, and toing. So we assume that the initial condition is not zero, but rather that we start from here, when it's moving, or maybe here, or wherever. Okay, and then what do we do, right? Because the x itself is different in this case. The conditions are different, and this is why we requires. Okay, I'll just show you the final form, which is in terms of the WD, which actually previously we talked about it. WD is the damping frequency, okay, plus the whatever initial condition. This is the initial condition, okay, alpha. Okay, if you were to also go and check it out your notes, okay, it also says that where is it? The constants R and alpha, P and Q depend on initial conditions. So when t is equal to 0, wherever, you get this. So the alpha itself will influence how the graph when it starts. Okay, so if the alpha has certain values, you will instead of at this position, it may be like starting from later position. Okay, so as I also as I mentioned, as I have drawn just now, if just only WD, okay, if just only WD, okay, if just only this equation, hold on a while. If just this equation itself, P and Q, although there is initial condition in it, is just describing the amplitude. Okay, it's just describing the amplitude, how high this amplitude is. Okay, but it didn't describe um where it starts. Okay, where it starts. Maybe it can start from here. Okay, then it start to go, or maybe it starts from here and then it start to oscillate up. You don't know how, right? So therefore you need a phase angle that could accompany with this thing to actually deal with the things. So in other words, when you're dealing with oscillations, okay, under them, the frequency itself, typically you deals with a complex system. Therefore we have I. This is why this is the third case where you have a lot of stuff. So I just don't want to complicate you, but rather than showing you the reason behind um, why we still need to continue and eventually um, sub in P and Q again. Eventually you sub in Q as R cosine theta and P equals to R sine theta. Okay, so this is what it is lah. Okay, yeah. So yeah. So this portion here, I talk so much about it, is just to tell you the reason why we want to sub P and Q as these two equations. Okay, if not, you also don't know what the fuck is this. Okay, so um I may be wrong also lah, yeah. So sub in the P and Q into this equation. Okay, so you're just simply subbing in, P equals to R cosine theta. I didn't change anything, so this is P and this is Q. The rest I didn't touch. Okay, I am innocent. So now you have sine and cosine, you have cosine and sine, which in certain sense is a trigo rule already, right? So the trigo rule says that if you have a sine, cosine, plus or minus cosine, sine, which is what we have here, luckily, therefore we can deduce that this is either sine A. If it's plus, then it is plus. If it's minus, then it's minus. So sine A plus B. In our place is plus, so it's sine A plus B. And therefore it is sine alpha plus the damping frequency time. Now we have this equation as this, right? This whole thing can be described using this formula. Therefore, when you sub it in, you have this equation. Okay, we just simply sub in this as this. And therefore, this equation, this portion over here, this function, describe the exponential form, the exponential graph of the graph itself, the final graph. And the R sine, whatever, describes the oscillation, the sine only. So when you multiply a exponential decay with a sine graph, you will find yourself with a very, I think you know what I mean, okay? So exponential graph and an oscillation, and eventually it will oscillate and dies down and decay. So this is what it means. And also, if you were to look at it properly, this is also the form of your third case scenario in your maths. Okay, your third case scenario in your maths is, although it's not explicitly defined in your thing, it's e rho t a cosine omega t plus b sine omega t. Right? This is a case 3 formula. It can alternatively it can also be rewritten as this one. But however, the cosine and the sine, okay, it all depends on whether your the phase angle lah, okay. I don't know how to describe this, but it is much related to this, okay. So they are related, and therefore this also explains why the general equation. This also explains why when our damping factor is lesser than 1, it's under damped, and under damped uses this formula. And please note that we are using this formula, okay, rather than this. And yeah, and you can easily attain the formula. So the previous video just now we talked about deriving all these things, and then if the question asks you to derive an underdamped equation, typically you have to first solve for A and B. Okay, so you have A and you have B, and you solve for initial condition. You sub it into your general equation. I think that you need to remember your general equation, and then after which you derive and derive, you eventually get this. And your R, if you don't know what the fuck is R, I also don't know. So okay, R is the amplitude. Okay, amplitude of the exponential curve, while the omega t plus, this dude over here is the phase angle, the phase shifting that I'm talking about. So R itself is much dependent on the initial condition of A and B, and then the R influence the amplitude, while the phase angle influence the frequency. Okay, and where it starts. So I hope it make a fairly clear understanding. And just to add on a little bit, just a little bit, is that what we are actually doing so far is to derive our equation for case 1, case 2, and case 3 if you were to see it properly. Okay, so although not described explicitly, okay, for this case we didn't describe explicitly, we say that we relate to case 2. But however, we are somewhat deriving from nothing to something, from the phenomenon, okay, from the very phenomenon of pulling the mass down and then you release. We can derive the three equation, the case 1 and case 2 and case 3 for our math, and therefore, just to summarize, I mean not summarize, but rather than end this series, I mean this case 2, is that um, this is our finalized form, okay, and then you will use this formula. Okay, I'm just going round round. So yeah, so this is the thing. Then yeah.